did I pronounce your name correctly? Yeah. Meng Tao? Okay, wonderful, excellent. Who's going to be talking about the sustainability of solar PV technologies.
Meng, are you going to talk to Dean to leave 5 minutes for questions?
Are you going to?
Probably 17 minutes.
17 minutes, okay, so we'll have time for a question.
Okay, yeah, good. Okay, excuse me. Now let's talk about the PV. And there is a misconception that solar energy is sustainable. We use solar energy, so we are sustainable. But the point I have been trying to make is that if the technology to utilize solar energy is not sustainable, we still do not have sustainable energy. So a couple of people I want to acknowledge, and also I have a book on this subject. This doesn't work. A couple years ago. So I will talk about several showstoppers to sustainable PV. And one is the limited availability of raw materials, storage of intermittent solar electricity, recyclability of waste solar modules. And I will also talk about a couple of bottlenecks to sustainable PV and high energy input to purify silicon, high cost at the system, module system infrastructure levels, and lower than ideal efficiency. And now the difference between a showstopper and a bottleneck is that a showstopper can completely stop us from moving forward, but while a bottleneck will slow us down but will not completely stop us. And based on this analysis, I will propose several strategic R&D directions for sustainable PV. And I have one slide on the research we are doing at ASU on sustainable PV. So this is a point which came up multiple times yesterday. That is the scale. The energy we use is enormous. And the projection is that by 2100, we'll need 46 terawatts of energy. That is, every second we need 46 terajoules of energy. That's a huge, huge, huge number. So from this, we can draw our first conclusion. That is, solar photovoltaics or any alternative energy technology must be deployed at a scale of tens of terawatts, or they will not make an impact on our carbon emission. And let's plug in some numbers. If we say a third of the energy will come from PV by 2100, that's 15.3 terawatts. Converting that into peak terawatts, that's about 100 peak terawatts total PV installation for a third of the energy we use by 2100. Now, the typical module time today is 25 years. That means every year, 4 terawatts peak of modules will die, and we need to produce 4 terawatts peak a year. So these are the numbers that we will have to be able to produce. Now, how much do we have now? By the end of last year, we have about 0.5 terawatts peak. So if we do end up with 100 peak terawatts by 2100, the industry has to grow 200-fold in the next 82 years. So that's a huge, huge opportunity. But even with this installation, we're talking about 1.4% of the global electricity capacity, which is PV. And remember, electricity only accounts for a third of the energy we use. 2/3 of the energy we use is chemical energy. So we're really talking about a very, very tiny fraction of the energy we use, which is from PV. Now, right now, we have 4 commercial technologies, and the dominant one is silicon, 95% market. Then we have 3 thin film technologies. They combined have 5% of the market. This figure shows the market share by different thin film technologies, and I want your attention to the light blue, which is cadmium telluride. In 2009, now it's a little fuzzy. In 2009, it had 13% of the PV market. And last year is 2.5% market. And hopefully by the end of this presentation, you will understand why cadmium telluride has been losing market share and why I believe it will continue to lose market share. And this is a figure from National Renewable Energy Laboratory. The different colors shows the different PV technology we have. We have close to a dozen PV technology today. And the horizontal axis is the time, and it shows the efficiency. So the reactor efficiency is actually 46%. But the workhorse is really these blue ones. Monocrystalline silicon about regular efficiency about 25%, and monocrystalline silicon about 20%. Then we have a little bit of these green ones, which are the thin film technology. Now, on one hand, we have a huge market to capture. On the other hand, we have about a dozen also PV technologies. So what is preventing us from just taking over that market? For many, many decades, and people thought that cost was the bottleneck to PV expansion. But cost is no longer an issue. Actually, according to the Department of Energy, by 2022, PV would be cheaper than coal electricity or nuclear electricity. So the question becomes, are we at the dawn of an explosive PV industry because the cost is no longer effective? And my answer to that question is, the answer is most likely no, because there are more fundamental limitations to this industry than just the cost. Let me give you one example. Remember, we make this device to produce energy, but it takes so much energy to make this device. This is the current industrial process to go from quartz to metallurgical grade silicon to trichlorosilane to polysilicon to ingot, wafers, cells, modules. Overall, it takes 30 kilowatt hours electricity to produce 1 watt peak of silicon module. Now, at the beginning of my presentation, I mentioned that when you produce about 4 terawatts peak a year, you multiply these two numbers, you compare to the current global electricity consumption, we are talking about half of the current global electricity consumption to produce 4 peak terawatts a year. Do we have that electricity? I don't know, but that's certainly a problem. Now, before I give you more examples, let me also talk about the requirements for a terawatt PV technology. I group them into 2 categories, material requirements and the device requirements. And the material requirements are for the cost and the scalability of the technology, and the device requirements are for the efficiency. Now, a comment I want to make is that the first silicon solar cell was demonstrated in 1954 from Bell Labs. So after 65 years, we still do not have a single semiconductor which meets all of these requirements. So nothing is actually perfect. All the semiconductors we have today miss 1 or 2 or multiple points here. So it becomes a pick and choose situation. If you say, I don't care how much energy I put in there, you can go with silicon, so you don't care about energy efficiency synthesis. Or if you say, I don't care about the availability of the raw materials, you can go with cadmium telluride. This is a really amazing technology. In 2007, the stock of First Solar went up 700%, and its production ramped up 25 times in 4 years between 2005 and 2009. But what will limit cadmium telluride in the future? If you check out this, U.S. Geological Survey publishes this mineral commodity summary every year. The total non-reserve of tellurium on this planet, total 24,000 tons. Now you can dig up every bit of tellurium, and also you know how much tellurium you need in each module, and you know the wattage of each module. So you can do that simple back of envelope calculation. We can produce about 0.5 terawatts peak. That's 0.16% of the 2100 energy demand. So cadmium telluride is not going to save us. Now this is really a best scenario analysis, because you know how much tellurium you put into a module, you know the wattage of the module, you know the reserve, and it's a simple calculation. But in this calculation, there are 2 assumptions. One is that we assume 100% material utilization, which cannot be true. We also assume infinite module lifetime, which cannot be true. So this is really a best scenario analysis, and the numbers I have here, you need to cut that in half. So you can do that for CIGS, cup indium gallium selenide. Indium is the problem. We can get about 1.1 terawatts peak from CIGS on the best scenario. That's 0.36% of the 2100 energy demand. You can do that with silver. We have about 500,000 tons of silver on this planet. You can get about 24 terawatts peak That's 7.7% of 2100 energy band, but realistically about 4%. So here's the summary. And out of the 4 commercial technologies, 3 of them suffer from material availability, and silver, tellurium, and indium. And if you add the voltage together, and that's about 8% of the 2100 global energy demand. Under the best scenario, realistically probably just 4%. The only technology which is terawatt capable is amorphous silicon, but for the last 20 years, amorphous silicon has been losing market share because efficiency is low, its cost is high. Now, it will be interesting if we cannot really have a terawatt PV technology, what will happen to amorphous silicon? That's an interesting question. Now we can also look at the annual production of raw materials because that really limits the deployment rate because that determines how big a solar panel we can produce each year. So that determines the deployment rate. So with tellurium, 550 tons a year, on the best scenario, we can produce 11 gigawatts peak per year of cadmium telluride, realistically 6 gigawatts peak per year. And First Solar is already producing 2.7 gigawatts peak per year. But remember, First Solar does not have access to all the tellurium on this planet. Let's say if it has access to half of the tellurium, we would be talking about 3 terawatts peak per year. So the room for growth for First Solar is really limited. Now you can do that for silicon cells, which use silver, and we produce about 26,000 tons of silver a year, and that gives us about 1.2 terawatts peak per year of silicon solar cells. CIGS indium is produced 820 tons per year, so 83 gigawatts peak per year. So here's the summary. Out of the 4 commercial technologies, the first 3, silicon, cadmium telluride, CIGS, combined on the best scenario, you can produce 1.3 terawatts peak a year, and realistically, probably 650 or 700 gigawatts peak per year. And again, now remember, we need to produce 4 terawatts a year, and amorphous silicon is the only technology which is terawatt capable. Now, coming to the next issue, showstopper, storage. Okay, sure. I see 2 showstoppers for in terms of storage. Now, a lot of PV systems are installed without storage. Those PV systems rely on the grid to serve as a reservoir, but the capability of the grid to serve as a reservoir is really limited. Let's say if it's 10%, then the current global electricity capacity is 5.5 terawatts, so that limits the PV capacity to 550 gigawatts. So that gives you about 3.7 terawatts peak if you add the grid-connected PV system without any storage. Now, the next showstopper is that if we use PV only for electricity, not nothing else but electricity, because only 1/3 of the energy we use is electricity, and among the 1/3 of electricity, there's still 5% which is hydropower, which does not need to be replaced. So you can do that simple calculation, and you end up with about 40 terawatts. That's the maximum amount of PV you can have if you connect PV to the grid and use PV only for electricity. Now, this also is another interesting question: is how big a battery do we need? Again, let's assume 1/3 of the energy comes from PV by 2100, and half of that actually needs to be stored. That's 1.8 times 11 kilowatt of electricity to be stored on a daily basis. That's equivalent of 500 laptop type battery for every person on this planet. We have 7.5 billion people. Every person needs a 500 laptop type of battery. It's an enormous size battery. Now, so this gets into, in my book, I have this reduced periodic table of Earth-bound elements. The cutoff is 100 millitons reserve, non-reserve. There are only 27 elements in it. The storage medium has to come from this table. Recycling. Now, recycling is a big issue, and if we do end up with 4 terawatts data modules each year, that's the size of New Jersey, which needs to be recycled. One thing I do want to point out is that there's quite a bit of financial incentives to recycle silicon modules. because the cells actually have much longer lifetime than modules. So if we can extract the cells out, that's quite a bit of revenue. If the cells are damaged, you can still extract the solar glycerin out, you can still extract the silver out. So you can produce somewhere between $12 to $30 per module in revenue by doing recycling. So I think recycling can be a profitable business without the government subsidies and cost. In the US, installation now is the biggest cost. 75% of the system cost is installation cost. And the storage is another issue. And all the numbers, the DOE side, they don't include storage. But if we add storage, the upfront system cost goes up 50%. The system efficiency goes down 30%. So you basically double LCOE by adding storage. And let me skip this one, module standardization. So here comes down to strategic R&D direction. Most of the current PV technologies are not sustainable. So strategic R&D directions include energy efficient purification of solar grade silicon, replacing silver with earth-bound element, profitable recycling of waste modules, module standardization. I did not have time to talk about that. And now we can also develop a future PV technology, but it has to be earth-abundant material, and since it has to be energy efficient, and the storage is a cross-cutting issue. So last slide, just talk about the research in my group. In terms of silver, we are looking at aluminum to replace silver. We developed a unique process called light-induced aluminum plating. And high energy input for silicon, we are looking at electrochemical refining to go directly from metallurgical silicon to solar grade silicon. If we're successful, we can cut down the energy consumption by 85% from the Siemens process. And the storage, we are looking at zinc oxide loop for storage. I noticed a couple of papers talking about aluminum. I think aluminum is not as good as zinc, and I have a paper on that. And the recycling, and we're trying to maximize the revenue from recycling. So we think we can get at least like $12 to $30 per module from recycling revenue. High system cost, we are looking at a new PV system based on load management. And for future PV technology, now this is a project we struggled a long time, and we have not made much progress. We want to use earth-bound metal oxide as the PN junction, but I really need to collaborate with a first principle person and also a material chemist on this project. So that's the last slide. So thank you.
Okay. We had a speaker, I believe it's Razi. Is he here? Okay, perfect. So we have a couple minutes for questions. So we still have 3 minutes for questions. So I can start but I want to give the audience the opportunity. Okay, wonderful.
Razi, quick question.
Thank you.
Yes,
of course.
Yeah.
Nasrin Khalili, IIT. We studied the availability of raw material and the price change and supplier risk. How do you see that play a role in solar power generation?
Yeah, I had that comment from somebody else before. When the price goes up, typically the reserve base goes up as well, because that means more difficult reserve cannot be dug up. But now the problem with this is that, talking about cadmium telluride, we're talking about 0.16% of the global energy demand coming from cadmium telluride. So that number, the reserve base needs to go up 100 times to really change my conclusion. So I doubt the tritium reserve would can be expanded 100 times. Now 3 times, 5 times, 8 times might be, but I don't think 100. But if we went anything less than 10 times more tritium, the solution is dead. Yeah. The conclusion is dead.
Okay, I think we have time for one other question. If nobody, there we go. There you go.
Thank you. Hi, Robert from Harvard University. Have you looked at iodine reserves?
Yeah, I just submitted a DOE concept paper and to look at iodine. Iodine, I think the reserve is about several million tons. So with the Provost guide, yeah, I just really need to look at the iodine consumption in Provost side before I can give you a definite answer. But yeah, iodine is more abundant than indium.
I think we had another, but just in the meantime, levelized cost of electricity, it's a limited metric. So what can you say about that with respect to your cost of solar and storage?
Yeah, I think eventually you have to not, in like California, in Arizona, in Nevada, without a storage, there's no point of adding more PV. So I guess you have to add a storage, then the DOE numbers in terms of cost of PV, you probably need to multiply it by a factor of 2. And then that changes a lot of things. And but so now we're also looking at what are the good ways for storage. Especially last year I was in Sweden, I noticed high level countries in summertime they receive as much solar energy as we have in Phoenix, but the wintertime they have almost nothing. So storage for like high electric countries really means yearly storage, summer electricity for future winters, or Arizona electricity for Sweden. That all batteries really don't work. We need a chemical storage for that. And then that's another issue of if you talk of LCOE. I don't know what LCOE that will be, but that's actually a solution needed.
Yeah, and it changes the system, so it makes it a very interesting question. So with that said, are we on to the next at this point? Okay, let's thank our speaker. I think that was a really great talk about the challenges of solar. Thank you so much. Razi is up next. Okay, perfect. I want to make sure that I'm pronouncing your name. Is it Nazi Nalim? Razi Nalim? Okay, wonderful. We're just setting up for Razi to speak. So he will be giving us a talk looking at cost reduction and scale expansion for structural carbon, which is a path to environmental decarbonization. We could have probably taken another question. I think we're still getting set up. Sure, yes, absolutely.
Can I just say it's very good to see that someone's looking at the recycling stage. I'm constantly concerned around what's happening and how we actually manage that transition. In Australia, we have so many rooftop PV at the moment, and I don't know what's going to happen in the 2025 year mark when they start to come off. We don't have any recycling in place, and I think it's a big problem.
No, absolutely, and it's also a problem here. I know that a number of our leading experts in solar are looking at it. Do you want to make one?
Yeah. One quick comment. And I know in EU you have this mandate to recycle modules. In US this year, DOE this new FOA does include recycling as a topic. Yeah.
Okay, so let's start with Razi.